Alright, greetings friends. Welcome to my video on volts, amps, and ohms. It's kind of ironically, I was just recording this video and the batteries on this tablet thing that I'm using to write died, which was kind of funny because I was talking about how batteries work and then mine stopped working. So I'm sort of starting over again because like the video got all messed up. But anyways, in this video I'm going to be covering these three items, these three sort of names that we use to describe electronic phenomenons, and they're sort of the building blocks of, try to fix this up a little bit here, the building blocks of electrical engineering, which I'm not going to go much more into detail than this video on that, because I'm not an electrical engineer, and I don't really know how to do that. But I do know the basics, and the basics are important to sort of understanding conceptually how electronics work. So, I got a message. Hold on one second. It looks like I'm destined to be interrupted on this video, but I'm just going to ignore that for now. And I'm going to do this. So what was I talking about? Okay, so I'm going to use volts. I'm going to use the analogy of a water tower to explain sort of how these concepts work. And I'm going to do that A, because it's a decent analogy, and B, because that means I get to call our circuits a series of tubes, which makes me happy. So I'm going to start with the basin, like a big tank of water, and that is sort of analogous to our battery, which we discussed in the last video, was sort of where our energy was stored, right? So in this water tower, we have a bunch of water that's just hanging out up there, but it's not really being used, right? And in our battery, we have a bunch of, charged electrons, positive and negative, that are sort of hanging out, and they're ready to do some work, right? They're ready to move electrons around, but they haven't yet. And that's what we call sort of potential energy, right? And that's what we measure in volts. Volts is the measure of potential energy. And that was discovered by a guy named Alessandro Volt. All these terms are named after the guy that sort of discovered that particular property, right? So Alessandro Volt discovered volts. I want to make sure I don't say invented volts, right? Because these things are natural phenomena. They exist before someone discovered they existed. They still existed. We just didn't know about them, right? So Andre Ampere discovered amps, yes, and George Ohm sort of discovered ohms, and also discovered Ohm's Law, which we will also go over. So that's this thing. We've got our volts. We've got our bucket of water, our big basin of water. We've got our battery that holds volts. And most typical batteries, like small batteries like this, are 1.5 volts. Obviously, car batteries and stuff have much more voltage. But left to its own devices, it's not really doing much. So the next thing we need to do is we need to connect something to it. And in our water analogy, we're going to connect a tube, right? And we'll connect a big, wide tube like this. And that's sort of analogous to our copper wire that we spoke of before, right? And we know that from the last video that copper is a very good conducer of electricity. It conducts electricity very well. And we can tell that this big, wide tube over here will allow lots of water to flow through it. So the amount of electrons or water that's allowed to flow through our material, right, our connected material here, is measured in ohms, which is a measure of resistance. I'm going to see if I can write a little neater here. Resistance. For some reason, like my thing's a little funky, but anyway, obviously, in this example, we have very low resistance, right? The less resistance we have, the wider our tube is, the wider we can think of as our tube being. And if we have like a smaller tube like this, right, that might be something like a human, right? Because human beings are also conductors of electricity to an extent, but we have a much higher resistance than a copper wire does. So that means that we allow less electrons to actually flow through, and that is what is measured in amperes, right, or amps. Amps is the amount of electrons, or the amount of water in our analogy, that's flowing through our circuit currently, right? So it's sort of our realized or actual energy. Like what is currently flowing through our system right now, right? And we can figure out how many electrons or how much water is flowing through our system based on like how much water is in here, how much water pressure do we have versus how wide is our tube, how much water is allowed to pass through at a time. And it's similar here. Our volts are like our water pressure, how much, sort of potential energy we have stored, and our ohms are representing how much resistance is in the material that our electrons are trying to flow through. And Ohm's Law states that our amps are going to be equal to our volts divided by our resistance. And I'm going to put an R here, although usually ohms are denoted by a little Greek symbol guy like that. But anyways, let's do some examples to sort of demonstrate how this works. So like the most extreme example would be a battery just sitting on the table, right? And we sort of said yesterday or last video, whenever that was, that this battery just sitting here isn't really doing anything. That's not exactly true. It's doing a little bit, but it's not doing much, right? Because there is a connection between the negative and the positive through the air, but the air has a very high resistance. But it's not, and our volts is 1.5, and our air resistance is very high, but it's not zero, right? Because if we think about like a lightning storm as such, right? What happens in a lightning storm is that a lot of negative particles build up in the atmosphere, right? And then the ground down below, the Earth, as we'll learn more in later videos, the Earth is actually a positive receptor of electrons, right? So all these negative particles would like to go to the Earth, but they can't pass through the air because the air has a very high resistance. Unless they build up to a certain, pressure, right? And then sort of like a bursting pipe, they overcome the air resistance and they come down and rain terror and destruction upon the populace, right? So it is possible to overcome air resistance, but it is a really big number, and a 1.5 volt battery is certainly not going to do that. But dividing a very small number by a very big number is going to give us some very small number that's effectively zero, but it's not actually zero. So there is like a tiny bit of electron transfer just going through the air, which is why even if you don't use a battery, if it sits around long enough, it'll just sort of go dead on its own, right? Although that takes a really long time. Now, the other sort of extreme example would be a battery that's just directly connected, or some power source. It doesn't have to be a battery, right? But some power source that's just directly connected with like a copper wire. Now, this is the opposite example because we still have 1.5 volts, but now we have very low resistance, right? And again, it's not zero, right? The resistance of copper is not zero, because if it was zero, you could just stretch a piece of copper all the way around the world and send signals back and forth. So obviously there is some place, there is some amount of distance where you've been going through too much copper, and even the resistance of copper is enough to not let your signal through, right? But we do know that, particularly in this example, right, that a very high, a relatively high number divided by a very small, decimal number is going to be some much higher number. So this is what's typically referred to as like a short circuit, right? Which a lot of your friendly neighborhood electrical engineer will try to avoid, because you may have heard that those are bad. And generally they'll do so by putting various like sort of things in here that are supposed to be specifically designed to be like resistors, so that your amps don't get too high and start frying your electronics, because obviously that would be bad, right? So those are pretty much the three basic building blocks of a computer or an electrical system, electrical circuits, right? Your potential energy, your energy source, right? Your resistance of the material that your electricity is flowing through, and then your actual amperes, like how many electrons are actually physically moving through your system at a given time, right? And those can be all calculated using Ohm's Law, or whatever version of Ohm's Law, right? We can multiply both sides by the resistance, and we can find out that our volts is going to be equal to our amps times our ohms, right? Or we could divide both sides by our amperes, and we could say that our ohms are going to be equal to our amps divided by our volts. So any of these combinations will work, right? And so depending on what we don't know, right, we can find things out.